Hi, my name is Eyoel Berhane. I'm going to be showing you how to be solving differential equations as linear systems. So for a quick review, the formula we have for a second order linear differential equation takes this form, where alpha, beta, and gamma are constants, and when we have this function, we make it equal to what we'll call f of t. Now there are two cases. One is a case where f of t is equal to 0, and there's not a homogeneous case, where it could be a constant besides 0 or a function. We're going to be working with a homogeneous case because of what we'll be able to do with it later on. So what I want us to think of is, can we represent homogeneous differential equations as linear systems? Because if we're going to be attempting to solve for them, we first have to see if we can represent them this way. And once we have that, what can we do with this representation? Can we be able to solve it as we are looking for? That's our goal for this video. So the first thing we want to do is assume a linear system and then attempt to convert it into a differential equation. So in order to obtain a singular second order differential equation, first let's start with the assumption. Assume that we have x of t and y of t, these two functions, with respect to time. Now we take the derivative of both of these functions, so we'll make them equal to these two equations, where a, b, c, and d are constants. So we want to form a simple, what I mean by a single differential equation, dependent on one variable. Now to do this, first what we want to do is separate out x and y. What I mean is, for one of these equations, we'll push the x's to the left side, and then for the other of these equations, we'll push y to the other side. So going right into that. For the first equation, let's isolate x. So let's subtract ax on both sides. This is what we get. And for the second equation, let's isolate y. So we'll subtract dy at both sides. Now next, we want to separate out the operations on the variables. So let's just take the first equation. What we want to do is take out that del operation and take out that a from the x, such that when we take those out, it's sort of like x is a constant multiplied with both of them. Turns out we can do this by bracketing out those operations in this form, where we have the del operation minus a in a bracketed form operated on the variable x. Now, because it can be second differential and third differentials for d over dt, it can be pretty confusing to follow through. So let's just term that as big D, such that when we take d squared and d cubed, we can treat those as second and third differentials, and so on. You can probably get the idea. So let us do that for the first equation. Then for the second equation marked in green, we'll do the same thing, but it'll be with respect to y. Then once we have both these equations in this bracketed form, set equal to 0, meaning we make all of these equations set equal to 0, this is the form it takes shape. This is important because, as we said, our goal is to make a single differential equation that is homogeneous. So, carrying those two equations over, what we want to do is, since we want a single differential equation focused on one of the variables, and seeing that we have two variables involved, what we want to do is to solve this system of equations by elimination, ridding of either x or y. Since we want y, we want to get rid of the x terms. Now, we want to apply operation on the first equation and apply an operation on the second equation, such that when we distribute those operations throughout the terms and then add all the terms down, the x terms, explicitly, since we want that eliminated, will cancel out. Now, we notice that, okay, one of the terms is positive, one of the terms is negative, opposite the equations. Now, we notice that x is operated with big D minus a for the first, and it's operated with c for the second equation. So let us multiply the first equation by c, since that's the operation on the second equation. Now, when we distribute that out to both of these terms, we see that since c is the operation of its own, we can treat that as a variable that we can distribute throughout that bracket of d minus a. So we can just make that c times big D minus ca. That's what it expands out to be. But we'll just keep that in mind as we go through this. And now for the second equation, we notice, okay, there's C being operated on X, but we don't have big D minus A. So we're going to apply that operation throughout that second equation for both of these terms. So what happens is that, okay, we have the big D minus A operate on Y, and both of those operations, which we'll do later, is that we treat those as sort of a factored sort of expression, where we're able to factor out those operations together, then later operate them on Y. But then for the X term using C, it's basically the same as the top first term that we had before, just now the C is on the other side. But it's the same term, just negative. So now that we can carry those over, we have, C minus D minus A, and then it's that same term but negative. We can just cross out those X terms because they're the same. We can add those down later on. Now we're all just left as the Y term, which is our goal. Next, we want to expand out the Y. To expand out those brackets and be able to put this all into one term for Y. So first is we're going to be focused on the second equation, where we'll distribute out those del operations. So since we're treating big D as a constant, we can multiply those D's together, make it D squared. Then we'll multiply A and big D, then little d and big D, multiply those together, and then A and little d together at the end to be positive. And since we have this C plus by at the top, we can just carry that down with the addition and then reinsert that into the operation. So this is the same as when we add those terms down. Then we want to expand this out further, just eventually get back a differential equation that we can identify. So since d squared, we treat that as second differential, that's just y prime. And then let's group little a and little d together to be a plus d. Because that'll be the constant for big D, which that'll be prime, and operator on y, that's y prime. And then AD minus BC is a constant that's multiplied with y. So this is what we simplify this out to be. Now this is important because this gets back to the idea of why we are choosing the homogeneous case, why this is useful. So bear with me of having this in the middle, but this is going to build upon what I'm going to be saying first. So when we are given that expression that we had at the beginning, just in the homogeneous case, we want to assume that we have some solution we'll call y to e to the r times t. Now, in this case, r will be the constant. Now, when we take the derivative of y, we know that basically we multiply the r down, so it'll be r to the e times r times t. And then when we take the second differential, we multiply it by another r down. And this is important because when we do this, and then we substitute that y back into the solution, we're able to divide that y out eventually, and this is the characteristic equation that we get. I know you don't see a lot of the algebra, but bear with me, that's how it eventually works out to be. Now this is important because we're going to be doing that for this expression below. But of course, instead of r, we're going to be using lambda. Now I say of course because you'll recognize that we use lambda to represent the eigenvalues of linear systems. This is why I'm using lambda. Now you'll be able to see that later on, but this is why lambda is going to be used for this. And with the substitution, as I was mentioning before, you can see why you'll be able to see why this does get us into the characteristic equation as we have. When we use the substitution for y, this is the expansion that we get out. Now we see, okay, e to the lambda is t, we know that's y. We can divide that y out because it doesn't affect the right side of the equation, and this is what we get. Now as you see, I have that slash polynomial at the title. Of course, as we see here, the characteristic equation turns out to be the characteristic polynomial set equal to 0. So with this information, we know, okay, we can identify a characteristic equation as a characteristic polynomial. So we can use this to attain solutions for differential equations. But before we get into that, first let's rephrase or convert our previous system that we had here into matrices that we can identify, just so we can easily see how these terms are laid out. So let us make the constant into a matrix we'll call A, and then let us put x and y into a vector that we call big Y. Now, when we take the differential of both of these, those two functions that we had together, then we'll have this expression, where we're taking a differential of vector y with respect to t, equal into this. And it's important because, as we were getting back to previously, we were able to get eigenvalues and eigenvectors. And remember from linear algebra, we get those from the matrix that we're given. So, before we get into using the eigenvalues, let's just rephrase quickly what they are. They're constants satisfying this equation where the eigenvectors, we'll call them VI, are non-zero. And they satisfy this equation. Now note that eigenvalues produce a specific set of eigenvectors. So when the eigenvalues are distinct, then the eigenvectors are also distinct. So from linear algebra, we know we are able to turn this expression, if we want to make it equal to some form of zero, in this case it's the zero vector, we'll have this expression of where the identity matrix is multiplied with lambda such that it's in the same dimensions, because we can't subtract constant from a matrix, but we can subtract it when the constant is multiplied with the same dimensions. So this expression we know we're able to get. And since because we want non-zero vectors for y, because we want to see what y is when y is non-zero, we want to prioritize our focus on a minus lambda times the identity matrix. And this is important because we could then make the ODEs homogeneous, which we have been working with all this time. Now, using the idea of negative lambda and the identity matrix, we know that the determinant of this turns out to be this expansion. And when we want to take the determinants, we multiply a minus lambda and d minus lambda together with the product of BC. Then we factor out what's in the parentheses out, and this is what we get. We recognize, okay, yeah, we got back the polynomial that we previously defined. So we know that getting the characteristic roots of the equation, the differential equation, once we put into the characteristic, then we know that's the same as getting eigenvalues and eigenvectors from a linear system. This is why this is important. So when getting the characteristic polynomial, it's much easier to reconvert it into that expression that we had before, just converting it back into the characteristic equation. So let's define all these constants with just much more simpler constants, just as 1. So we'll call alpha to be 1, since that's the constant for lambda squared. Then we'll make beta be the quantity negative a plus d. So that's what the expression will be for beta. And then gamma is just our constant at the end. So we reform that characteristic equation that we had. So with this, we know that when we want to get roots from polynomials, and in this case it's second degree, we know when we want to get those solutions, we use something called the quadratic equation, where lambda is both of these values, where one is when we're adding that square root, and then one is we're subtracting that square root. But these are both of these solutions. So we know there are 3 cases. The real case is when the square root is more than 0. We know that because it produces a real number, so adding, subtracting, that produces 2 distinct real numbers. Then when we deal with a repeated case, the square root turns out to be 0. So we're not adding or subtracting, but we're having a case where this eigenvalue is being repeated. So that works out to a bigger expansion than something else. And the complex deals with when the square root is less than 0. This involves the use of our variable I, which represents the square root of negative 1. Thank you for listening, and if you want to learn more about this, here's a website that'll help you expand upon how these cases work out and any other things that I didn't describe in this presentation. Thank you.